Okay, now we're going to look at what's called belief network inference. So what we're interested in doing is determining the posterior distributions. So the distribution of variables when after we've observed other variables. And we're going to look at in graphical models of which Bayesian networks are belief networks are just one particular type. So here are some methods we're going to use. So a few methods that are used are sort of variable elimination is a method. And there's a dual method called recursive conditioning. So variable elimination is a dynamic programming method, and recursive conditioning is the search variant of it. What we're going to do is exploit the structure of the network to eliminate, which means sum out the non-observed, non-query variables one at a time. So that's one class of methods. It's a systematic method. We're going to sum them out. Just like in CSPs, we also have methods that to use randomness. So here we're going to look at stochastic simulation. So random cases are generated according to the probability distribution, and we're going to use those as samples to estimate other probabilities. Some other methods are variational methods, which we're going to try to find the closest tractable distribution to the distribution we're interested in. But that's because the previous methods are often finding exact ones is computationally hard, so we're just going to approximate them. And a large class of them called variational methods. And there are other methods which are bounding approaches, which bound the conditional probabilities above and below, and you iteratively reduce the bounds. So what we're going to look at first of all is this idea of variable elimination. So you can abstract this problem into just thinking about what are called factors. So a factor is a representation of a function from a tuple of random variables into a number. I'm going to write a factor just as is f of x1 to xn. So just thinking this is a factor that takes in the values of the random variables and produces a value. Okay. And here's some operations we're going to do in factors. So we want to work out what we're going to do. So we can assign a value to a variable. So we can assign f of x1 is equal to v1 is now just a fact. Now we're only looking at a factor. It only depends on these remaining variables. So we can assign one of the values or more of the value, and then it's only a function now of the remaining variables. Okay. And if you assign all of the values, you just get a number. And this number is the value that of f arises when x1 is assigned v1 and x2 is assigned v2 and xj is assigned vj. So one of the ways of thinking like this is just the normal notation of functions you've seen before. It's just instead of writing them in positional notation where the first position, the second position, the third position, we're going to write them using named positions. So it's just like a function. We just can have named. We just can have named positions, and that turns out to be very convenient for what we're doing. And also, we're going to write it with the assignment, the value as a subscript. Okay, so as an example, so we could write R of x, y, z as a table. We're given a value for x and a value for y and a value for z. Here we're assuming the values of x are either t or f. And so these are all of the 8 assignments to the values of x, y, and z. Okay, and this one here says, if x is true and y is true and z is true, the value of this is 0.1. Right, we look at this one down here. Whoops. We look at this one down here. This one here says that if x is false and y is true and z is false, then the value of this function is 0.6. So we can assign a value to the variable. We can assign r of x is true is now just a function of y and z. It just takes the top 4 rows, because they're the ones with x is true, and it says that function of y and z. So the value of true is the value of x is true, y is true, z is true. The value of true false here is x is true, y is true, z is false. Right? X is true, which is 0.9. Okay? And we have x is true, y is true. So x is true, y is false, z is true is 0.2. X is true, y is false, and z is false is this one, it's 0.8. We can assign two values. We can assign x as true and z as false, and that's just a function of y. Okay, it's just a function of y, and we look at x as true, z as false, which is this one, and we look at the true case, gives us 0.9. And similarly, the false case gives us 0.8, and we can assign all three, and it's not a function of any nut values, it's just a number. So that's how factors work. Okay, we can multiply factors. So now we're going to look at two factors, f1 on x and y, and f2 on y and z, where y is it's a tuple of variables. So x and y can be disjoint tuples of disjoint variables. So y are the variables in common. So an x are the variables in f1 that aren't in f2, and z are the variables in f2 that are not in f1, and y is the variables in common. So the product of these is a function of all of the variables, and it's defined by just for given all of the variables, we're just going to multiply out. We're just going to project it onto f1 and multiply it by f2. So here's an example of doing this. Suppose we have f1 as a function of a and b, and f2 as a function of b and c. Then f1 times f2 is a function of all three. So it's a function of a and b and c. And if we want to multiply them, well, we're going to look at this one. We're going to project this onto f1, which is true, true, so you get 0.1. I'm going to project this onto b as true, true, so that's 0.3. So multiply them together and get 0.03. Okay, so this one here is f. For the next one here is the true, true, false one is true, true is 0.1 times true, false is 0.7. So that's why it's 0.07. Let's look at this, true, false, true. So true, false is 0.9, and false, true is 0.6. So you multiply those together and get 0.54. Okay, so that's all we're going to do. We're going to keep multiplying these corresponding values, and false, false, false is just look at false, false is 0.8, and false, false here is 0.4, and you multiply those two together, you get 0.32. The other operation we're going to look at is summing out a variable. We can sum out a variable, say x, and suppose the range of the domain of x is v1 to vk from this factor, and we're going to result in this factor on. So the resulting factor is now just depends on all the other variables. So if we sum out x1, we get a variable on this. So we're just going to do f is x1 plus and all the other ones. Just going to sum out over all the values of x. Okay, so here's an example of doing this. We're going to sum out b, and that's if you sum out b from this factor of a, b, and c, we just get a factor on a and c. Okay, so it's not a factor of b anymore because we've summed it out. And when a is true and c is true, we're going to just sum out all the values for b. So here's one value with a is true and b is true. So 0.3 plus 0.54 gives us 0.57. If you want to do a is true and c is false, we're going to look at all the a is true, c is false. It's 0.07 and 0.36. And we're going to add those together and get 0.43. And similarly the other ones. Okay, they're the basic operations on this. So here's some ways to think about what are these factors over. If you can think about what's going to happen here, it's sort of interesting to play with. Okay, so now we can just treat, this is just the normal notation we have for conditional probabilities. So if you want to compute the posterior probability of z given this assignment of values to y, it's the probability of z given y1 is v1 and yj is vj. Well, that's the product of z and this one here, and this assignment given the probability of y1 to yn. Okay. And so this one here, the bottom one, is just summing out z of this. It's just marginalizing out z. So this bottom one is just summing out Z of this. So the computation reduces, if we could compute this, then we can compute this. We just have to sum out Z, we just have to normalize. Okay, so now we're going to look at how to compute this value. Now suppose all of the variables are x1 to xn. What we'd like to do is we'd like to produce the probability of Z given y1 is v1 and yj is vj. So we're going to introduce all the other variables. So in fact, the z's are going to be the non-observed variables in this. So there's this variable, this z here, and all the others are the non-observed variables. So we're just going to have z as a special one of the non-observed variables, and these are the other non-observed variables. And we're going to partition all these zi into some elimination ordering. So what we're going to do is we're going to say the probability of z, so this is what we're interested in computing. And what we're going to do is we're going to introduce all the other variables, we're going to sum them out. So that's the probability now of all the variables x1 to xn with this assignment of values to variables. Okay, so we introduce all the other variables and sum them out. But why we did that is we know what this is, because this is just this conjunction of values to variables. So we can compute that as the product of xi given the parents. So it's probability of xi given the parents. So this probability of this joint probability is the product of all of these values. And we're going to sum out the variables. Okay, so this is the big sum over products. So how can we compute sums of products? So computation is reduced to computing the sums of products. And here's the sum of products. You're going to compute AB plus AC efficiently. Well, you could do it directly, and you have two multiplications, one addition, but you can do it better than that. We can do it better than that by distributing out the A, and we get one addition and one multiplication. Okay, so that's simple and straightforward. It's something you would have learned in high school. And that's all we're going to do. So what we're going to do is we're going to think about computing Z1 times this big product of xi given the parents of xi. What are we going to do that efficiently? We're just going to distribute out the factors that do not include Z1. So distribute out the factors that do not involve Z1. And we're going to multiply. All right, so that's what we're going to do. So now summary, to compute this product of x given Z, y1 is v1 and yj is vj, we're going to construct a factor for each conditional probability. We're going to set the observed variables to their observed values. We're going to sum out all the other variables according to some elimination orders, and we're going to multiply the remaining factors. And then we're going to normalize by dividing by f of z, the resulting factor, by summing out z. So that's what we're going to do. We're going to compute this conditional probability by computing the probability of the conjunction, and then we're going to normalize at the end. And how do we sum out a variable from a product? That's the only remaining thing in here we don't know how to do. We need to, this is the complicated thing, how to sum out each of the other variables. So to sum out a variable from a product, we're going to partition the factors into those that don't contain zj. So we're summing out zj. We're going to those factors that don't contain zj and those that do contain zj. And to sum this out, we're going to distribute all the ones that do not involve zj out of it, multiply all those ones that do contain zj, and sum out zj from this. So we're only going to compute in here. And so we're going to explicitly compute a representation for this factor here. We're actually going to evaluate this factor. So let's look at an example of this. Here is the belief network. So we have all these variables, and we want the probability of E given we've observed G. So if we do that, what's the probability of E and G divided by the probability of G, which is summing out of E of the probability of E and G. And we're going to introduce all the other variables, and I'm going to put this into some elimination ordering, which is all the other variables are D, A, C, F, and B. I'm going to put them in this order. The order work counts, by the way. And we're going to have the product of all of these factors. So it's the probability of A times the probability of B given A. So these are all the factors to find the the conditional this distribution. So it's the probability of A given its parents, which is stay, B given A and C, the probability of C, D given C, E given B, F given E, and G given E and D. Okay, so that's all the factors that define this belief network. And now we're going to look at how to sum out D. So now what we'd like to do is to sum out D. So the only ones that matter are in here. The only ones that we need to work to do is the summing out D is the fact that this contains D and this contains D. And everything else can be ignored when we're summing out D. Okay, so we're going to end up there with summing out D of D given C and G given E and D. And this is a factor only on C and E. Okay, this is a factor on C and E. Now we're going to sum out A. So we've summed out D. Now we're going to sum out A because we're actually going to go from the inside out. Now we're going to sum out A. And sum out A, the only factors that contain A are this one, and there's an A in there, and there's no other A in here. So we're going to end up with this other two factors, and these two can be multiplied separately. They don't interact with each other. Okay, we can now sum out C. What contains C? Well, these have been summed out. This contains C, and this has also been summed out, so this is down here. So this one contains C, okay, as well as this one. So we're going to sum out C from this product of these three factors. We've got these three factors, we're going to multiply them together and sum out C. Now we're going to sum out B, and which factors contain B? Well, I think we've used up all of the probability of E given B is one we haven't yet summed out, and we end up with this factorization. If you now sum out F, we'll find out that F, the probability of F given E, we can just sum it out because it's only contained in one factor. And that hasn't appeared, this factor here does not contain E. So here's our factorization. So in variable elimination, we're going to start from the middle, this inside out, and compute this recursively. Okay, here's another example. It's basically the same way of doing it. So if we want to produce G given F, we're going to introduce all the other variables and then sum them out. And you end up with another factorization that tells you how to do it. And this is going to be much smaller than summing out all these things together. So multiplying all these together gives the enormous factorization. But this one here, all the factors are actually not too large in here. So all the factors are not too big. Okay. So we're going to talk about this in class this week and next week.